What do you think happens to a person sealed in a metal tube for 3 full years? Not 3 weeks in orbit? Not a 6-month ISS rotation? 3 years of pure void? What happens to bones when gravity stops pulling on them for 1,000 days straight? What happens to a brain? No day, no night, no season, just recycled air and hum. What happens to memory, to vision, to the heart, to the mind, to sanity itself? People used to say the biggest Mars mission challenge would be fitness and boredom. Early NASA documents from the 1970s described deconditioning as manageable and temporary. Astronauts came back soft, did months of physical therapy, and reportedly returned to normal. That was the comfortable story for decades. It was essentially the only one being told. It seemed reasonable, the way deep-sea diving once seemed like just swimming with gear. Then divers started dying from the bends, a condition nobody predicted because nobody measured. Today we have measurements, decades of them. And what they reveal is genuinely disturbing. The human body was not built to survive what a 3-year Mars mission demands of it. Not temporarily inconvenienced, not briefly impaired, structurally and neurologically altered. This is not a screenplay. This is physiology, biochemistry, and peer-reviewed neuroscience. And it explains why NASA has never announced a firm crewed Mars launch date in 50 years. Not the funding, not the rockets, not political will. The problem is the body inside the ship. In 2013, the Curiosity rover carried the RAD instrument on its transit from Earth to Mars. RAD, Radiation Assessment Detector, measured something no instrument had ever captured before. For the first time, scientists had direct data on what interplanetary space does to human tissue. The research team received the numbers and ran the calculations a second time to be certain. Every single day in deep space, a human body absorbs approximately 1.8 millisieverts of radiation. That number needs a reference point to land with the weight it actually deserves. The average person on Earth accumulates that same dose across 2 full years of ordinary life. A Mars-bound astronaut receives it every 24 hours, every day, 700 times the terrestrial rate. Over a 3-year mission, the accumulated total reaches approximately 1 sievert is not a guideline. It is where NASA officially labels radiation risk as unacceptable. At 1 sievert, a person's lifetime fatal cancer probability rises by roughly 5.5%. NASA's full-career radiation limit for ISS astronauts is 600 to 1,200 millisieverts total. That range accounts for age and sex, calibrated to keep added cancer mortality below a ceiling. A 3-year Mars mission burns through that career limit before the crew reaches Mars orbit. This is not a nuanced edge case. It is arithmetic, producing one clear and uncomfortable answer. Under NASA's own safety rules, a 3-year crewed Mars mission is currently technically illegal. Not politically complicated, not underfunded, illegal by the agency's own adopted standards. That sentence never appears in press conferences, and that silence says everything. Radiation is the opening chapter of this story. It is not remotely the darkest one. Begin with muscle, the failure mode most people have at least heard mentioned before. 6 months aboard the ISS. 2 mandatory hours of structured exercise every single day. Resistance harnesses, ergometers, treadmills with vacuum suction to simulate gravity loading. 2 hours of dedicated daily training, and astronauts still lose roughly 20% of muscle. 20% gone in 6 months, despite training specifically designed to prevent exactly that. The mechanism is not insufficient effort. It is the complete removal of gravitational load signal. Every moment you stand or walk on Earth, your muscles receive constant mechanical demand. That demand sends a continuous biochemical signal. Maintain mass, stay ready, preserve strength. Remove gravity and the signal disappears. The body reads absence as permission to dismantle. Measurable atrophy begins within 72 hours of microgravity exposure, detectable at cellular level. By the end of the first month, losses become functionally significant for physical performance. 6 months yields a 20% reduction even under the most aggressive countermeasure protocols. 3 years to Mars and back is territory no human biology has ever entered and survived intact. Models built on ISS data project 30 to 40% of total skeletal muscle lost across 3 years. 30 to 40% is not mild deconditioning. It is atrophy, that redefines physical capacity. The crew arriving at Mars after 9 months of transit must immediately operate in a full EVA suit. That suit masses over 130 kilograms on Earth. Even at Martian gravity, 0.38 grams, it is a real load. The person inside will have spent 9 months losing muscle despite completing daily exercises. Stand, walk across the habitat, lift a sample case, respond to a pressure alarm in 30 seconds. Every one of those actions demands strength the body has been quietly dismantling since launch day. Muscle does eventually recover, slowly, imperfectly, but recovery remains at least possible. Bone tells an entirely different story, and that difference defines the gravity of the situation. The human skeleton loses 1 to 2% of structural density every month in microgravity. 1% monthly sounds minor until projected across the full length of a 3-year mission. 12 months at that rate yields roughly 12% total bone mineral density reduction. 36 months projects to a loss of 30% or more, depending on the individual person. Osteoporosis, which fractures elderly hips, is clinically diagnosed at around 25% loss. A healthy 32-year-old astronaut could land home with the skeletal profile of a 70-year-old patient. What makes bone loss worse than muscle loss is this: some of the damage does not reverse at all. Post-mission studies found permanent residual bone deficits in astronauts after year-long missions. The lumbar spine, the femoral neck, the tibial shaft all showed lasting structural alteration. Not a temporary shortfall fixed by rehab, a permanent change in microscopic bone architecture. Scott Kelly spent 340 days aboard the ISS in NASA's Year in Space study from 2015 to 2016. His twin Mark stayed on Earth, identical genetics, completely divergent biological experience. When Scott landed in Kazakhstan on March 1, 2016, changes were documented across every major system. His bones, his cardiovascular output, his visual acuity, his immune markers, his gut microbiome. His telomeres, the end caps linked to aging, had lengthened measurably during the mission. Then, within months of return, those same telomeres shortened rapidly, an unexpected stark reversal. Published analysis found roughly 7% of Scott's gene expression had not normalized by 2019. 3 years after landing, nearly 1 in 15 genes still expressed differently than pre-flight. That study examined a 1-year mission. A 3-year mission has no comparable human data at all. Nobody has spent 3 years in deep space. Nobody has measured what that timeline does to the body. ISS data gives researchers a foundation. Extrapolation extends it into unmapped, uncertain territory. Beyond a certain mission duration, projections become principled estimates, not verified facts. What the data confirms is that damage is not linear in its progression, it accelerates over time. The body does not adapt to microgravity and stabilize. In critical systems, degradation continues. Bone density does not plateau at month 6. The skeleton keeps losing structure month after month. The crew arriving at Mars will not be diminished versions of the people who left Earth's orbit. They will be biologically altered, changed in bone, muscle, cardiovascular function, and brain. The most alarming recent findings concern none of those systems. They concern the brain directly. In 2022, a Nature paper reframed how researchers understood cognitive risks of deep space travel. The study exposed subjects to radiation calibrated to match Curiosity's RAD instrument readings. Not an approximation, the actual dose rates recorded during the Earth to Mars transit phase. Memory performance dropped by approximately 30%. Reaction speed fell by a comparable margin. 30% is not marginal. In clinical neurology, it constitutes a significant neural event. The researchers pinpointed the target precisely: the hippocampus, central to memory formation. The hippocampus is not a passive storage drive. It is the organ that builds new memories from life. It generates spatial maps. It encodes new learning. It is the architecture of adaptation itself. Hippocampal damage does not erase existing memories. It degrades the ability to form new ones. A person with this impairment navigates unfamiliar environments less reliably and responds slower. The radiation erodes the hippocampus gradually, invisibly, across months of continuous exposure. By the time the crew nears Mars, 9 months of neurological degradation has already accumulated. They are cognitively different people from those who launched, measurably, neurologically changed. Now they must manage the most complex machinery ever sent to another planet without live support. Every critical call carries a communication delay of 4 to 24 minutes each direction. No real-time consultation, no expert guidance from the ground. Every decision made independently. Decisions made by a crew whose hippocampi have absorbed 9 months of interplanetary radiation. This is the mission profile that vanishes from the animations of red terrain and gleaming habitats. The renderings show confident astronauts in pristine suits striding across the Martian horizon. They omit the bone density charts, the muscle loss curves, the neurological impairment assessments. They do not show what one accumulated sievert does to the structural biology of a human being. That is the Mars mission nobody will discuss openly. This documentary will discuss all of it. The eyes go first, not metaphorically, literally, structurally, measurably. Long before the crew reaches Mars, something is happening inside their skulls every day. Cerebrospinal fluid, the liquid cushioning the brain, has no gravity to drain downward. On Earth, it pulls toward the feet during the day and redistributes gently during sleep at night. In microgravity, it shifts permanently toward the head and stays there. For months. For years. The pressure inside the skull rises slowly, almost imperceptibly, over weeks of exposure. That pressure presses against the back of the eyeballs from the inside, gently, relentless. The optic nerve sheath swells. The retina flattens. The focal length of the eye changes. Astronauts returning from the ISS have documented blurred vision, trouble reading instrument panels. Some could not read printed text without corrective lenses they did not need before launch. Dr. Noam Alperin at the University of Miami imaged astronaut brains before and after long missions. His 2017 study in the journal Radiology showed measurable flattening of the eyeball in long-duration crews. The condition has a name, spaceflight-associated neuroocular syndrome. Researchers call it SANS. SANS is not rare. As of 2021, roughly 70% of astronauts on long missions develop it. 70%. More than 2/3 of people who spend extended time in microgravity go blind. Not permanently, but significantly enough to impair precision tasks during the mission itself. Imagine the scenario. The crew is 9 months into transit. A navigation sensor needs manual reset. The procedure requires reading a sequence of alphanumeric codes from a panel 2 feet away. The commander squints, the numbers blur. The cerebrospinal fluid shifted 3 months ago. This is not a hypothetical failure mode, it is a documented outcome with a published incidence rate. The engineering team that designed the display did not design it for eyes reshaped by space. NASA's Human Research Program listed SANS as one of 5 top health risks for Mars missions in 2020. Not as a footnote, as a primary obstacle, a problem without a fully validated solution today. Nutrition complicates every single one of these problems simultaneously and invisibly. The human gut does not function the same way in microgravity as it does under terrestrial conditions. Gastrointestinal motility slows. Absorption rates for key nutrients shift unpredictably over time. Calcium absorption, critical for offsetting bone loss, becomes measurably less efficient in space. Vitamin D synthesis stops entirely because there is no sunlight penetrating the hull of the ship. Without sunlight, the body cannot produce vitamin D regardless of how much it consumes in food. Vitamin D governs calcium metabolism, immune function, muscle repair, and bone density maintenance. Every system already under stress from microgravity is now running on a depleted nutritional base. The ISS receives resupply missions regularly: fresh food, new nutrient formulations, updated provisions. A Mars mission carries everything it will consume for 3 years in the hold at the shelf life becomes a hard constraint. Freeze-dried food loses measurable nutrient density over time. Studies on ISS food stores found vitamin content degrading by 20 to 50% within 12 to 24 months. After 2 years, certain vitamins exist in food packets primarily as degradation byproducts. The crew in year 3 is eating caloric material that no longer delivers its labeled nutritional value. They are exercising, repairing tissue, fighting radiation damage, all on food that has quietly failed. This is not a supply logistics error, it is a fundamental limitation of current food science. Nobody has developed shelf-stable nutrition that maintains full potency for 36 consecutive months. The combination of these factors, radiation, microgravity, nutrition, SANS, does not add linearly. They interact, they amplify each other through shared mechanisms in overlapping biological pathways. Radiation damages the gut lining, which reduces nutrient absorption, which worsens bone loss. Fluid shift increases intracranial pressure, which strains the cardiovascular system, which drops output. Muscle loss reduces metabolic demand, which slows rehabilitation after bone fractures, which extends injury. The body is not experiencing 4 separate problems, it is experiencing one cascading systemic failure. Dr. Charles Lomoli at UC Irvine has spent years mapping radiation's specific effects on the central nervous system. His team has published more than 40 peer-reviewed papers on space radiation and brain degradation. In 2018, he summarized his findings in an interview with the journal Scientific American simply. He said, "The problem with space radiation is not that it kills cells. Cells can be replaced. The problem is that radiation permanently alters the behavior of surviving cells in unpredictable ways. Neurons that survive bombardment by galactic cosmic rays do not function the same way afterward. Their dendrites retract. Connections between neurons simplify. The network grows." Cognitive testing in irradiated animal models showed deficits in problem-solving and spatial reasoning. Not memory alone, executive function, the higher-order thinking required for command decisions. The commander of a Mars crew is not just remembering checklist items when she decides to abort a landing. She is synthesizing sensor data, crew status, weather patterns, fuel margins, and risk assessments. That synthesis requires dense, complex neural architecture, exactly what radiation progressively simplifies. Dr. Lomoli's work did not appear in NASA press releases about Mars, it appeared in academic journals. The gap between what the research says and what public communications acknowledge is significant. Consider the psychological dimension, which receives less quantitative attention but demands equal weight. 6 people, a volume roughly equivalent to a modest apartment, 36 months, no exits. The same 6 faces across every meal, every exercise session, every engineering failure, every argument. The same 6 voices in the audio feed, on the comm channel, in the bunk section after lights out. Human beings evolved in groups that fractured when tension rose. Someone left, the dynamic shifted. On a Mars transit vehicle, nobody leaves. The group cannot fracture, the tension has nowhere to go. NASA has studied analog missions at isolated research stations to simulate aspects of this confinement. High seas. The Hawaii Space Exploration Analog and Simulation ran crews in domes for up to a year. Researchers documented the phenomenon called third quarter effect, a predictable morale crash. The third quarter of any isolated long-duration mission reliably produces a spike in psychological distress. Motivation drops, interpersonal conflict increases, engagement with mission tasks declines measurably. For a 9-month transit to Mars, the third quarter falls approximately around months 6 and 7. That places the psychological nadir at precisely the moment the crew is furthest from any rescue. Not near Earth, where psychological support can intervene with additional communication bandwidth. Not near Mars, where the destination provides motivational structure and immediate purpose. In the middle of interplanetary nothing, at maximum communications delay, at maximum psychological vulnerability. The 2010 Mars 500 simulation ran 520 days in a Moscow facility, the longest isolation study ever conducted. 6 international crew members simulated a complete Mars mission: transit, surface, return. The research team monitored sleep, activity, mood, and interpersonal dynamics across the entire period. Published findings showed dramatic individual divergence within the crew as the mission progressed. One participant developed near-complete social withdrawal, spending most waking hours in his bunk. Sleep disorders emerged and persisted across the entire second half of the simulation experiment. Chronic sedentary behavior appeared despite mission protocols specifically designed to prevent it. And this was a simulation. The participants could have walked out through a real door at any moment. The ground crew was reachable by phone in real time, no communication delay, no actual void outside. A genuine Mars mission removes every one of those psychological safety nets simultaneously. The void outside the hull is real, the delay is real, the impossibility of turning back is real. Dr. Nick Canis at UC San Francisco has studied space psychology since the Mir era in the 1980s. His book Space Psychology and Psychiatry, now in its 3rd edition, documents the patterns clearly. Crew-to-crew tension typically exceeds crew-to-ground tension as missions extend beyond 6 months. The group turns inward. Interpersonal dynamics become the primary psychological reality for the crew. Subtle behavioral incompatibilities that seem trivial during a 6-month mission compound over 3 years. The way someone chews, the way someone laughs at the wrong moment, the way someone handles bad news. In the context of total confinement with no exit, these micro-irritants become sources of real conflict. Managing that conflict requires psychological intervention, and the crew's therapist is on Earth. With a 20-minute round-trip communication delay, there is no such thing as real-time counseling. The crew resolves its own psychological crises with degraded cognition in a metal tube, alone. Sleep disruption feeds every other problem and accelerates every other degradation simultaneously. The human circadian rhythm is governed by light, specifically by the 24-hour cycle of day and night. Aboard a Mars transit vehicle, that cycle does not exist unless it is artificially simulated perfectly. ISS astronauts experience 16 sunrises per day as the station orbits Earth every 90 minutes. Their circadian rhythms fragment, sleep quality drops, hormonal regulation tied to sleep degrades. Cortisol, the stress hormone regulating immune function, inflammation, and glucose, loses its rhythm. Irregular cortisol means irregular immune function, irregular healing response, irregular stress threshold. A crew member who sleeps badly for 3 years does not arrive at Mars tired, they arrive damaged. Sleep deprivation at chronic levels produces cognitive impairment comparable to measurable intoxication. Studies published in Sleep Journal found 17 hours of continuous wakefulness equals a blood alcohol of 0.05. A crew averaging poor sleep quality accumulates functional impairment equal to mild chronic intoxication. Add radiation-induced hippocampal degradation on top of chronic sleep impairment and the picture sharpens. The crew managing the most complex machinery ever built is cognitively compromised by multiple independent mechanisms. Cardiovascular changes add another layer that the fitness narrative of astronauts tends to obscure. The heart is a muscle. Remove the load of pumping blood against gravity, and it begins to atrophy too. Cardiac output drops measurably within weeks of microgravity exposure as the heart works less hard. The left ventricle, the primary pumping chamber, becomes measurably smaller after extended missions. Scott Kelly's cardiac imaging showed structural remodeling after 340 days that required months to reverse. A 3-year mission projects structural cardiac changes beyond anything currently documented or studied. The heart returning to a gravity environment after 3 years faces a demand it has forgotten how to meet. During landing, during the physical exertion of a return entry, the cardiovascular system is critically tested. Orthostatic intolerance, inability to maintain blood pressure when standing, is universal after long missions. Every astronaut returning from the ISS requires assistance standing. Many faint within the first hours. For a Mars return, there is no medical team at the landing site. There is no landing site team at all. The crew must execute a powered atmospheric entry, a landing sequence, and immediate suit removal independently. Their bones are compromised, their muscles are depleted, their hearts are smaller than they were at launch, and they must do all of this on Earth, where gravity is 2.6 times stronger than what they experienced on Mars. The return is arguably more dangerous than the outbound journey, yet receives a fraction of the attention. The immune system deserves its own chapter, and the research on it is quietly one of the most unsettling. Spaceflight dysregulates immunity through at least 3 distinct mechanisms operating simultaneously. Radiation directly damages immune cell populations, particularly the T cells that coordinate immune response. Cortisol dysregulation from disrupted sleep weakens the immune signaling cascades that coordinate defense. Social isolation and psychological stress further suppress immune function through well-documented pathways. The result is a crew with progressively diminished ability to fight infection across the mission duration. Dormant viruses that the immune system normally suppresses begin reactivating in the microgravity environment. In 2019, NASA published a study showing that Epstein-Barr virus, herpes simplex, and varicella zoster, all 3 reactivated in astronauts during and after ISS missions at measurably elevated rates. These are viruses that live permanently in human nerve tissue and are held dormant by healthy immunity. Healthy Earth-based immunity, not the degraded, radiation-damaged, sleep-deprived immunity of deep space. By the second year of a Mars mission, the crew's viral load situation could be genuinely precarious. An outbreak of shingles, varicella zoster reactivation in a confined crew is a medical emergency. The infection is painful, debilitating, and transmissible. 3 years from a hospital, in a metal box, the mission carries a medical kit. It does not carry a physician. It carries a crew member with medical training. That crew member's cognition has been degraded by radiation. Their judgment has been blunted by sleep loss. They are treating their crewmate's medical crisis with impaired decision-making in a compromised environment. There is a term used in human factors research for the compounding of multiple degraded systems under stress. It is called performance deficit stacking, where each individual impairment multiplies rather than adds. A pilot who is mildly sleep-deprived and mildly intoxicated does not fly with 2 mild impairments. The combination produces a deficit far greater than the sum of its parts in critical decision scenarios. The Mars crew is not facing one performance deficit. They are facing at minimum 5 or 6 simultaneously. Radiation, cognitive impairment, sleep disruption, cardiovascular deconditioning, muscle loss, each one measurable individually in combination. Across 3 years, the interaction effects are unknown. No study has examined this combination systematically because no human has survived it to be studied. This is the empirical vacuum at the center of Mars mission planning. The data simply does not exist. Engineers can model thermal loads on a heat shield. Materials scientists can test hull integrity at pressure. Physiologists cannot model 3 years of cascading human degradation because they have no reference population. Every calculation extrapolates from shorter missions and animal studies into genuinely unmapped territory. The Mars mission community is aware of this. The conversations happen in workshops, in journal supplements. Dr. Dorit Donoviel directs the Translational Research Institute for Space Health at Baylor College of Medicine. Her institute was specifically created to bridge the gap between space health research and mission reality. In a 2021 interview with Space.com, she described the situation in straightforward terms. She said that for a mission to Mars, the radiation problem alone could be disqualifying without new solutions. The current state of radiation shielding technology cannot reduce the dose to acceptable levels. Water shielding, the best passive option available, adds so much mass it makes the mission economically impossible. Polyethylene shielding reduces some radiation types, but is ineffective against high-energy galactic cosmic rays. The particles that penetrate everything, stripped atomic nuclei traveling at relativistic speeds. They pass through aluminum, through polyethylene, through water, and through the human skull unimpeded. High-Z shielding materials like lead and tungsten reduce dose rates, but cannot be carried in sufficient quantities. Active magnetic shielding, generating a field to deflect charged particles, remains conceptual and untested. The engineering mass required for a functional magnetic shield around a crewed habitat is enormous. No tested solution currently reduces interplanetary radiation exposure to within NASA's own safety. That is not a research gap waiting to be filled. That is a hard engineering constraint today, in 2024. And so the mission, as currently conceivable, remains technically illegal under the rules the agency wrote. SpaceX has spoken openly about sending humans to Mars in the early 2030s aboard Starship vehicles. Elon Musk has described the radiation risk as acceptable because volunteers would understand the danger. The phrase he has used is willing to die for it, a characterization that bypasses the regulatory framework entirely. But medicine does not answer to rhetorical framing, however compelling or sincerely motivated it may be. The cancer risk does not decrease because the volunteer accepts it philosophically. The dose is the dose. The hippocampal degradation does not spare participants who signed waivers. The physics are indifferent. Willingness is a legal and ethical framework. It does not alter biochemistry or cellular damage thresholds. The conversation SpaceX is having is about consent and courage. The conversation medicine is having is about biology. Both conversations are real. Only one of them is subject to physical laws that cannot be overridden. None of this means Mars is unreachable. It means Mars is unreachable on the current trajectory. The gap between where human space medicine stands today and what a Mars mission requires is specific. It is not vague institutional resistance or risk aversion dressed up as science. It is particular problems. Each one has a potential solution. None of those solutions exist in validated, deployable form today. The radiation problem needs either biological countermeasures or shielding that hasn't been invented. Pharmaceutical approaches are being investigated, compounds that accelerate DNA repair after radiation damage. Amifostine, currently used in cancer radiotherapy, shows partial radioprotective effects in cell studies. Bio300, a synthetic form of genistein, demonstrated protective effects in primate radiation studies in 2020. Neither drug has been tested in the specific context of continuous low-dose chronic interplanetary radiation. The dose profile in space, continuous, low-rate, high-energy, is fundamentally different from radiotherapy. Cancer patients receive acute high-dose bursts. Astronauts would receive a chronic slow drip for years. Whether drugs that protect against the former can protect against the latter is an unanswered question. The bone loss problem has a conceptual solution that has been tested partially. Artificial gravity. Rotate the spacecraft or a section of it, generate centrifugal force equivalent to a fraction of Earth's gravity. Even 0.5 grams generated through rotation would dramatically reduce the loss of bone and muscle density. Soviet research in the 1980s on short-arm centrifuges suggested partial gravity could halt most bone loss. The engineering constraint is that rotation introduces gyroscopic effects that complicate navigation control. A rotating habitat section connected to the main spacecraft requires complex transfer mechanisms at the joint. No space agency has ever flown a rotating artificial gravity module on a crewed mission in actual space. The concept has existed for 60 years, from the discovery in 2001. A space odyssey to today. The engineering has never been prioritized sufficiently to move from concept to tested hardware. If artificial gravity were available, bone loss and muscle atrophy projections change substantially. Without it, projections remain what they are, a cascade that begins on launch day and does not stop. The cognitive problem may be the most difficult because it operates at the intersection of multiple causes. Radiation damages neurons directly. Sleep disruption degrades consolidation. Isolation affects executive function. Addressing any one of these without addressing the others produces partial mitigation at best. The crew needs better sleep, which requires better light management, better sound insulation, better scheduling. The crew needs cognitive support, which requires psychological infrastructure that does not currently exist. The crew needs reduced radiation exposure, which requires technology that does not currently exist. Solving Mars means solving all of these simultaneously, not sequentially, not one at a time. The interaction effects that multiply individual impairments mean partial solutions produce partial protection. A crew with solved radiation but unsolved sleep dysfunction is still cognitively degraded on arrival. The systems are interconnected. The solutions must be interconnected as well. Nothing about this is simple. Dr. Jennifer Fogarty served as the Chief Science Officer of NASA's Human Research Program for years. In a 2019 interview, she described the Human Research Challenge as the most complex NASA had ever faced. Not because the problems were individually intractable, because they were so deeply interdependent. She said, "You cannot fix the radiation problem without knowing how it interacts with the nutrition problem. You cannot fix the nutrition problem without knowing how it interacts with the gut microbiome changes. You cannot fix the microbiome problem without knowing how it interacts with the psychological changes. The entire system is coupled. That is what makes it hard in ways that rocket engineering is not." Rocket engineering operates in a domain where failure modes are understood and bounded by known physics. Human physiology in a novel environment operates in a domain where the failure modes are still being discovered. What the ISS Year in Space study did for the field was begin mapping the true scope of the problem. Before Scott Kelly, researchers thought they understood the extrapolation from 6 months to 12. After Scott Kelly, they understood that the extrapolation was less reliable than they had assumed. Gene expression changes that persisted 3 years post-mission were genuinely unexpected by the research team. Nobody had predicted that 7% of a human genome could still be dysregulated 3 years after returning. If 12 months produces 3 years of genomic alteration, what does 36 months produce? There is no Scott Kelly equivalent for a 3-year mission. No data, no reference point, no answer. The Mars planning community works with projections built on incomplete foundations, and they know it. The honest documents, the internal NASA reports, the peer-reviewed supplements, the working group, they use phrases like residual uncertainty and insufficient longitudinal data and extrapolation beyond validation. Translated, we are guessing about the outer limits of what 3 years in deep space does to human bodies. Educated, rigorous, peer-reviewed guessing, but guessing nonetheless because no one has done it yet. This matters beyond mission planning. It matters for what kind of society decides to send humans to Mars. There are two distinct conversations happening in parallel about human Mars exploration right now. One conversation happens in aerospace engineering communities, in rocket design studios, in propulsion labs. It is largely optimistic, technically grounded, focused on timelines and launch windows and vehicle mass. The other conversation happens in human physiology labs, in space medicine clinics, in neuroscience departments. It is more cautious, more qualified, more focused on what happens to the people inside the vehicles. The two conversations do not often occupy the same stage at the same time in public forum. Press conferences about Mars timelines do not typically feature presentations on hippocampal degradation. Launch event live streams celebrate engineering milestones. They do not feature bone density projections. The asymmetry is understandable. Engineering triumphs are visible and celebratory. Biology is slow and grim. But decisions about whether to send humans to Mars require both conversations in the same room simultaneously. The rocket either reaches Mars or it does not, a binary outcome that engineering can define and predict. The human either arrives cognitively intact or does not, a gradient outcome that medicine is still measuring. Funding shapes what gets solved. Priorities determine which problems get the engineers and which get the memos. NASA's Human Research Program operates on a budget that represents a small fraction of total NASA spending. The human biology problems receive resources. They receive far fewer resources than propulsion and structures. The result is a development trajectory where the rockets become flight-ready faster than the biology gets solved. That asymmetry could produce a situation where a technically capable rocket carries a physiologically unprepared crew. The mission can launch, whether the people inside it can perform when it matters is the open question. Returning to the surface of Mars itself, the moment the renderings always celebrate adds new dimensions. Mars has 0.38 grams, roughly equivalent to what a person weighs at the bottom of the ocean on the deepest shelf. After 9 months of microgravity, the crew's musculoskeletal system is not adapted to 0.38 grams. It is adapted to nearly zero gravity, a state that took months to reach and cannot be reversed in hours. The initial days on the Martian surface are a transition period for which there is no directly relevant data. Researchers can estimate based on ISS return data transposed to a 0.38 grams environment, but that is a transposition. The bones compromised by microgravity now bear load again. Stress fractures are a documented risk. A hairline fracture in the tibial shaft of a crew member on the first EVA is not a manageable inconvenience. There is no surgeon, there is no imaging suite, there is no transfer to an orbital medical facility. There's a crew with basic medical training, a pharmaceutical kit, a surgery manual, and each other. The communication delay to Earth, now at its maximum of 24 minutes each direction, precludes real guidance. By the time a surgeon on Earth finishes describing a procedure, the situation may already have changed. Medicine on Mars is medicine practiced by non-physicians under cognitive impairment in an alien environment. The training can be excellent, the preparation can be thorough. The biology does not care about preparation. A bone that was 30% less dense than normal when it fractured takes longer to heal under any conditions. In a nutritionally compromised, radiation-damaged, sleep-deprived organism, healing is slower still. The margin for error in every physical action on the Martian surface is thinner than mission profiles typically project. And the surface stay itself, depending on mission architecture, lasts somewhere between 30 and 500 days. The shorter the surface stay, the more the total mission radiation dose concentrates in transit time. The longer the surface stay, the more biological adaptation problems compound on the Martian surface. Mars has a thin atmosphere that provides essentially no radiation shielding compared to Earth's magnetosphere. The Martian surface adds its own radiation dose on top of the transit dose, lower but still significant. Curiosity has measured average surface radiation at 0.64 millisieverts per day at Gale Crater. That is roughly 230 millisieverts per year on the surface, still many times higher than Earth's annual average. A 500-day surface stay adds roughly 320 additional millisieverts to a crew already near its career limit. The total mission dose approaches 1.3 sieverts, significantly past the threshold where NASA says stop. Habitat construction partially mitigates this. Underground habitats or regolith-covered shelters reduce surface dose. But the first crew cannot live underground immediately upon landing. They must build the shelter first. They build it while wearing EVA suits that provide minimal radiation protection, with compromised muscles, with degraded cognition, with bones that are structurally weaker than when they left Earth's orbit. The first weeks on Mars represent a period of maximum physiological vulnerability combined with maximum workload. Everything the mission requires in those early days demands peak performance from a crew at biological nadir. This is not a design flaw that better mission planning can fully resolve. It is a sequential constraint. The landing happens after the transit. The transit degrades the crew. The crew must perform upon landing. The sequence cannot be reordered. The biology cannot be paused and restarted at a convenient moment. What would an honest mission briefing for a Mars crew actually contain, presented without editorial softening? It would begin with the radiation consent form, specific, quantitative, unambiguous about cancer probability. Your lifetime fatal cancer risk increases by a minimum of 5.5%, possibly more depending on solar activity. This risk cannot be reduced to zero by any technology currently available for deployment aboard this vehicle. You will absorb more radiation than NASA's own safety standards permit. There will be no exemption on return. It would continue with a cognitive disclosure. By the time you reach Mars, your memory will be measurably impaired. Not subjectively, measurably, testably, documentably impaired relative to your baseline cognitive assessment. Your reaction time will be slower, your spatial navigation will be less reliable, your executive decisions may be affected. These deficits will compound throughout the surface stay and the return journey. Full recovery is not guaranteed. It would address the skeletal reality. Your bones will be structurally compromised upon landing at Mars. You will be at elevated risk for stress fracture during EVA activities for the first weeks on the surface. We do not have a validated countermeasure that prevents this. We have protocols that reduce the probability. It would cover the psychological dimension. Your mental health will be under the most sustained pressure ever studied. Conflict within the crew is statistically predictable based on every isolation study ever conducted. You will be more than 24 light minutes from Earth and psychologically on your own during the hardest moments. And it would close with the return. When you land back on Earth, you will not be the person who launched. Your genome will still be expressing differently than it was before departure, possibly for years to come. Your bones may never fully recover to your pre-mission baseline. The evidence suggests some deficit is permanent. Your heart will struggle against Earth gravity for weeks or months as cardiovascular function rebuilds. None of this is designed to discourage you. It is designed to ensure that your choice is genuinely informed. Has any agency ever delivered that briefing in that form to a crew being considered for Mars? The answer is no, because no crew has ever been formally assigned to a Mars mission that was actually approved. The conversations exist in research papers, in workshop proceedings, in working group reports marked internal. They do not yet exist in the form of a specific signed consent document handed to a specific named astronaut. When that document exists, it will be one of the most extraordinary pieces of text in human history. A human being reading the complete medical reality of their choice and signing their name to it anyway. That act, that signature, will require a kind of courage that has no precise historical equivalent. Explorers have always accepted danger. Shackleton's crew accepted the possibility of death in the Apollo 1 crew accepted risk aboard a spacecraft that ultimately killed them on a launch pad in 1967. Chuck Yeager accepted unknown aerodynamic forces when he pushed the X-1 past Mach 1 in 1947. But those risks were externally imposed, incompletely understood, discovered by accident, or discovered mid-mission. The Mars crew will sign a document that says, "We know exactly what will happen to your brain, your bones, your eyes. We have measured it, we have quantified it, we have published it in peer-reviewed journals. And you're choosing to go anyway, with open eyes that will be structurally deformed within 6 months of departure." That is a different category of courage. Not braver than those who came before, different in quality. The courage of choosing a fully understood and quantified biological sacrifice in service of the species. Whether civilization is ready to ask that of individuals, and whether individuals are ready to offer it, is not a scientific question, it is a moral one, and the science has already done its part in defining the terms. The history of medicine is full of moments where the honest answer was, "We do not yet know how to protect you, Surgeons in the 1840s operated without anesthesia and without sterile technique because neither existed. Pilots in the 1940s flew without ejection seats because the engineering hadn't been completed and validated. Radiologists in the early 1900s lost fingers and hands to X-ray exposure before dosimetry was understood. Every frontier generates its victims, people who advanced human knowledge at personal biological cost. The Mars frontier will do the same if it is opened on the current timeline with current countermeasures. The question is not whether to go. The question is when, and whether the biology has been solved first. Going before the biology is solved means accepting that the first crew serves partly as a research population. Not a secret research population, a publicly acknowledged one, but a research population nonetheless. They will generate data that no animal study, no Earth-based analog, no simulation can generate. They will tell us what 36 months of deep space actually does to the human body at a resolution we currently lack. And they will pay for that knowledge with their bones, their memories, their immune systems, their eyes. Future crews will benefit from what the first crew documents through their own biological experience. This is how medicine has always advanced at its outer edge. The ethics of that precedent are uncomfortable. They are also the historical reality of how humanity has extended its presence into every new domain. The children of the first Mars crew will know their parents came back different, not broken, different. Changed in ways that the mission medical team will study and document and publish for the benefit of others. That is the covenant that underlies exploration at the biological frontier. It has never been clean. It has never been free of cost. It has never been something that could be done without someone paying first. What has changed is that we now know the cost in advance, with more precision than any previous frontier. We know the sievert count. We know the bone density projection. We know the hippocampal degradation curve. We know the immune suppression data, the telomere behavior, the gene expression timeline, the SANS incidence rate. The data exists. The question is who reads it, and whether what they read changes the timeline, the technology, or just the consent form. There is a version of the Mars mission that addresses these problems before it launches. It has artificial gravity to arrest bone and muscle loss during transit. It has validated radiation shielding. It has pharmaceutical countermeasures for cognitive protection tested through clinical trials, not animal models. It has food science that maintains full nutritional potency for 40 months, not 18. It has psychological support infrastructure that functions across 24-minute communication delays. It has a tested rotating habitat that humans have actually lived in for at least a year without degradation. That mission does not exist today. Not because any of its components are physically impossible, because none of them have been funded to completion, validated, and certified for human spaceflight. The version that exists today is a capable rocket, a plausible trajectory, and a set of unsolved human problems. The gap between those two missions, the one that is ready and the one that is currently buildable, is not measured in engineering years. It is measured in medical research funding and genuine institutional priority. If the human body problems receive the same resources as the propulsion problems, the timeline changes. Not immediately, not in 5 years, but the trajectory bends in a different direction than it currently points. Dr. John Charles spent 25 years at NASA's Johnson Space Center as a human research scientist. He contributed to the Twin Study, the Year in Space Research Architecture, and multiple countermeasure studies. In a 2020 interview, he described the state of human research readiness for Mars with measured precision. He said, "We know enough to know we don't know enough. That sounds circular. It is actually important. Knowing the boundaries of your ignorance is different from not knowing anything. We know where the gaps are. The gaps are specific, the gaps are measurable, and the gaps can in principle be closed with sufficient effort. Sufficient effort has not yet been applied. That is a choice. Choices can be changed." Something about that statement deserves to sit without elaboration for a moment. The gaps can be closed. That is not optimism. It is an engineering and scientific assessment. The gaps have not been closed. That is not a failure of capability. It is a failure of prioritization. A species with the technical sophistication to design and land a precision rover on another planet in 2021, a rover that deployed a helicopter drone on an alien world in its 3rd operational week. That species is not incapable of solving the bone loss problem or the radiation shielding problem. It has chosen not to apply sufficient resources to those problems relative to the vehicle problems. The rocket is spectacular. The human inside the rocket is under-resourced. That imbalance has a cost. And the cost will be paid, eventually, by the specific individual human beings who they will pay it in bone density and radiation dose and hippocampal degradation and immune suppression. They will pay it willingly, if the current trajectory continues, because they volunteered and they understand. Whether we, the civilization that sends them, have done our full duty by solving what was solvable before asking, that is the moral question that the medical data makes impossible to avoid. The renderings of Mars will continue to show red rock landscapes and gleaming habitat modules under alien stars. They will continue to show astronauts striding purposefully across the rust-colored surface in pristine suits. Those images are honest about the destination. They are selective about the condition of the travelers. The destination is real. The landscape is magnificent. The scientific return would be the travelers will arrive with impaired memory and weakened bones and reshaped eyes and diminished immunity. They will arrive as profoundly brave people who accepted a quantified biological cost we could describe in advance. And what they do on that surface, damaged, altered, cognitively changed, will still be extraordinary. Because the capacity of human beings to accomplish extraordinary things in compromised circumstances is perhaps the one variable in this entire equation that no laboratory has ever managed to fully measure. The radiation will do what physics says it does. The biology will respond as physiology predicts. But the person inside that biology, the one who chose to be there, who trained for this, who signed the form, that person is not fully described by any set of measurements we currently possess. Human motivation and purpose, and the capacity to act in service of something larger than the self, operate in dimensions that bone density scans and hippocampal imaging do not fully capture. This is not a reason to ignore the biology. The biology must be solved. Every solvable problem must be solved. It is a reason to hold both things simultaneously, the hard physical reality and the extraordinary human agency. The Mars mission nobody wants to talk about is the one where a human being arrives at a red planet. With 30% less bone density than when they left, memory impaired by 9 months of radiation, eyes reshaped by a year of intracranial pressure, immune system running on reserves, sleeping badly for 3 years. That mission is the one being planned. That crew is the one being recruited. Not in some distant imagined future. In a present where the rockets are real and the medicine is incomplete. The conversation that needs to happen in public, in full, with the data on the table, is whether that is acceptable, and if not, what specifically must be solved before it becomes acceptable. That conversation is the one that gives the mission its actual meaning. Not the landing, not the flag, not the first boot print in Mars. The conversation, honest, complete, uncomfortable, that happens before the hatch closes. Because the universe does not negotiate with ambition. It enforces its physics without exception. Every system in the human body was shaped by 300 million years of evolution inside Earth's gravity and magnetic field. No generation of that evolution occurred in deep space. None of it prepared for this particular problem. The body that evolved to walk savannas and climb trees and run from predators across an African landscape is being asked to survive a 3-year transit through the most hostile radiation environment it has ever encountered. That gap between what evolution built and what the mission demands is the central biological fact. Closing it requires not bravery. Bravery is already guaranteed by the people who are willing to go. Closing it requires science, funding, time, and the institutional honesty to say, we are not ready yet. And the discipline to stay with that honesty long enough to actually become ready before the hatch closes. There's one more dimension that mission planners discuss even less than the medical data. What happens to a human identity when it has been 3 years between you and the world you came from? Not distance in kilometers, distance in time, distance in shared reference, distance in belonging. The crew that lands back on Earth will have missed 3 years of history, culture, and ordinary life. 3 years of news cycles, of music, of the deaths of people they loved, of births they couldn't witness. Their children will have grown in ways that photographs and video calls cannot fully transmit. A parent who left with a 6-year-old child returns to a 9-year-old they essentially do not know. The relationship that existed at launch was built on daily physical presence, meals, bedtimes, ordinary routines. Video calls across 24-minute delays cannot preserve that. Letters cannot rebuild it across 3 years of silence. The family on Earth also changed, it adapted, it found equilibrium without the crew member at the table. And the crew member returning is not the person who left. not just emotionally, but neurologically, physiologically. Reintegration for returning long-duration astronauts is already a documented psychological challenge. Scott Kelly described difficulty reconnecting with crowds, with traffic, with the sensory volume of ordinary life. After 340 days, he found the weight of his own arms strange, the smell of rain unexpected, crowds overwhelming. A 36-month crew will encounter reintegration challenges that no returning astronaut has yet experienced. The scale of neural and psychological adaptation required is genuinely without precedent in human history. The society they return to will have moved on as societies do with or without them in its narrative. They will be heroes. Their faces will be on screens, their names will be taught to school children, and they will stand on Earth feeling the weight of their own bones for the first time in 3 years. Trying to remember the dream they had last night, struggling with recall, knowing it cost them something, looking at a family that is simultaneously theirs and no longer entirely theirs in the way it once was. That moment, not the landing, not the boot print, is the true endpoint of what a 3-year Mars mission does. The physiological degradation is real. The psychological cost is real. The relational cost, none of these costs invalidate the mission. Human history is a record of costs paid for things worth having. The question worth asking, the question that all the data eventually circles back to, is simpler than it looks. Is the civilization that sends them ready to deserve their sacrifice? Are the solvable problems actually solved? Because if they are not, then what gets sent to Mars is not just a crew, it is a preventable casualty. And preventable casualties in any domain of human endeavor are a failure of the people who could have prevented them. The ISS has been continuously inhabited for more than 24 years as of this writing. 24 years of unbroken human presence in low Earth orbit, a stunning operational achievement. The data accumulated across those years is the most comprehensive dataset on human physiology in space ever assembled. It is also, paradoxically, data gathered in the safest possible version of spaceflight, protected by Earth's magnetosphere. The ISS orbits at approximately 400 kilometers altitude, well within the Van Allen radiation belts that deflect cosmic rays. Astronauts aboard the ISS receive roughly 1 millisievert per day, significant compared to Earth, but a fraction of deep space. The moment a vehicle leaves Earth's magnetic protection and enters interplanetary space, the dose rate jumps immediately. Everything learned on the ISS about bone loss, muscle atrophy, cardiovascular change, and immune function. All of it was learned in a radiation environment dramatically kinder than the one a Mars mission enters on day 1. The ISS is the laboratory, the transit to Mars is the exam. The lab conditions were not the exam conditions. That gap between ISS radiation and interplanetary radiation means ISS data systematically underestimates Mars risk. Extrapolating from ISS to Mars is like extrapolating marathon performance from training runs on a treadmill. The treadmill gives real data about the runner. It does not replicate the conditions of the actual race. Nobody at NASA is unaware of this distinction. It appears explicitly in the technical literature, but public communication of Mars missions rarely foregrounds the distinction with the clarity it requires. The renderings do not include a label reading. This crew will experience 4 times the radiation dose of our best data. That label would be accurate. Its absence in public communication is a form of selective disclosure. Dr. Tor Straum at NASA Ames Research Center has spent decades studying heavy ion radiation effects on cells. His work focuses specifically on the high-energy galactic cosmic rays that no shield currently stops. In a paper published in the journal Radiation Research, he summarized the core problem with straightforward language. He wrote that the biological effectiveness of high-energy heavy ions, the HZE particles, remains poorly understood. Their tissue-specific damage patterns, their interaction with pre-existing cellular states, their long-term consequences, all of these remain active research questions without sufficient data to produce reliable projections. The uncertainty is not in the dose measurement. RAD measured the dose accurately during Curiosity's transit. The uncertainty is in the biological response to that dose, what specific damage it causes, and how severe. The dose is known. The consequence of the dose at the cell and tissue level is still being determined. That is a different kind of uncertainty than the engineering uncertainties around propulsion or life support. Engineering uncertainties yield to testing. Build it, fly it, measure what fails, redesign and test again. Biological uncertainties about novel radiation exposures yield only to exposure, which cannot be tested ethically. You cannot ethically expose human subjects to Mars-level radiation in a controlled study to measure consequences. The data will only come from people who actually make the transit, people who consented to the exposure. This creates a loop that cannot be broken without someone going first and reporting back what happened to them. Every piece of biology data from a Mars transit will be generated by people who were simultaneously the researchers and the subjects. That dual role, consenting experimental subject and mission crew member, is unprecedented in human medical history. Clinical trials separate researchers from subjects for reasons that are fundamental to ethical science. The Mars mission cannot maintain that separation. The crew is the trial, the mission is the study. The results come back in the form of the crew's returned biological state, their bones, their brains, their blood. Published, analyzed, applied to the next mission, the scientific cycle completes through the crew's sacrifice. There is no clean way to frame this. Medicine has a term for individuals who accept risk to advance knowledge for others. They are called research pioneers. The history of medicine treats them with reverence and occasionally with guilt. The physicians who deliberately infected themselves with yellow fever to prove mosquito transmission in 1900. The cardiologist Werner Forssmann who threaded a catheter into his own heart in 1929 to demonstrate cardiac catheterization. The gastroenterologist Barry Marshall who drank a solution of H. pylori bacteria in 1984 to prove it caused ulcers. Each of these people accepted specific, known biological risk in service of knowledge that benefited others. The Mars crew will be in their lineage, people who advance human knowledge through personal biological cost. What distinguishes them is scale. The cost is larger, the risk is more systemic, and the alternatives were more fully explored. Marshall drank a bacterium that could be treated with antibiotics if his hypothesis was correct and he became ill. The Mars crew absorbs a cumulative radiation dose that cannot be treated retroactively if the consequences are severe. The biological debt is permanent, whatever the magnitude turns out to be. That is the weight behind the data. Not just numbers on a chart, a debt paid by specific human named people. People with families and histories and favorite songs and opinions about the best coffee on Earth. People who will spend 3 years in a metal tube doing something that has never been done and cannot be undone. The mission will happen. Perhaps not in the 2030s, perhaps not with the specific vehicles currently being built. But the trajectory of human exploration has never reversed permanently in response to known biological risk. Humans crossed the Atlantic knowing people died. They dove to depth knowing pressure could kill. They entered Antarctic winter knowing the cold was survivable, but not safely. They flew knowing the physics was new. Mars will be added to that list. The question of when is a question of when the medicine catches up to the ambition. And if it doesn't catch up in time, if the ambition outpaces the medicine and the mission launches anyway, the first crew will still go knowing what the data says. Having read the consent form with full information, that choice, made freely and with complete information, belongs entirely to them. What belongs to the civilization that asks them to make it is the obligation to solve what is solvable first. To fund the research, to validate the countermeasures, to fly the rotating habitat test, to complete the pharmaceutical trials, to build the mission worthy of the people willing to fly it, not just the mission capable of reaching the destination. The destination is a red dot 225 million kilometers away at closest approach. The journey is the complete biology of a human being under conditions it was never evolved to encounter. Both deserve the same rigor, the same funding, the same public honesty. The rocks of Mars have waited 4 billion years for someone to pick them up and read what they record. They can wait a few more years while the biology gets solved.